Welcome to The Explainer. Today, we're going to crack open one of the most important science books ever written, Stephen Hawking's A Brief History of Time. So over the next few minutes, we're going to trace humanity's incredible journey from ancient myths all the way to the bleeding edge of modern physics to see how we've tried to answer the biggest questions out there. Where did this universe come from? And, what's our place in it? So Hawking starts his book with this great little story. A scientist finishes up a lecture on astronomy, and this woman stands up and says, "That's all wrong. The world is a flat plate on the back of a giant tortoise." The scientist, a bit amused, asks, "Well, what's the tortoise standing on?" And she just replies, "You're a very clever young man, but it's turtles all the way down." It's just a perfect, funny way to show our earliest mythological attempts to make sense of the cosmos. So how did we get from giant tortoises to the Big Bang? Well, we took a huge leap. We moved from telling cool stories to using a structured, rigorous scientific method. And that, right there, was the game changer. And this gets to the absolute core of what makes science different from myth. See, a good scientific theory doesn't just explain what we've already seen. It has to make bold, specific predictions about the future. Predictions that you can actually go out and test, and, this is the crucial part, that can be proven wrong. If you can't prove a theory false, it's just not science. Okay, let's jump ahead to our first really great scientific picture of the universe. And for that, we have to thank Isaac Newton. For the first time, the cosmos wasn't some chaotic place run by unpredictable gods. Nope, it was a grand, predictable, beautiful clockwork machine. For thousands of years, thanks to Aristotle, we all thought the Earth was special. It was the center of everything, and its natural state was to be perfectly still. Newton just completely shattered that idea. His laws proved there's no such thing as absolute rest. It doesn't matter if you're playing ping pong on a moving train or standing by the tracks, the ball follows the exact same rules. All motion is relative. And for more than 200 years, this Newtonian view gave us a really comforting picture of the universe. It was eternal, it was infinite, and it was fundamentally static, unchanging. Space was this absolute, unmoving grid, and time was like a universal clock, just ticking away at the exact same rate for everyone, everywhere. But this neat and tidy picture had some really serious problems. I mean, think about it. If the universe is static and infinite and just filled with stars, then no matter where you look in the night sky, your line of sight should eventually hit a star. The whole sky should be a blinding wall of light. So why is it dark? You know who else saw a huge crack in this bottle? Newton himself. He realized that in an infinite universe, the pull of gravity from all those countless stars should have pulled everything into one giant clump an eternity ago. A static universe should have already collapsed. The clockwork machine was broken. To fix it, we didn't just need a small adjustment. We needed a revolution. And the answers came from a complete demolition of our old ideas about space and time, all delivered by one person, Albert Einstein. Einstein's theories of relativity basically just threw out Newton's absolute stage. Space and time weren't these separate, rigid things anymore. No, they were woven together into a single dynamic four-dimensional fabric called space-time. And this fabric could be bent and stretched and warped by mass and energy. Now here is the big, revolutionary leap. Einstein said that there is one thing in the universe that is absolute, the speed of light in a vacuum. It's the cosmic speed limit, and it's the same for everybody. But think about what that means. If speed is just distance divided by time, and the speed of light is always constant, then distance and time can't be. They have to be flexible. They have to stretch and shrink depending on how you're moving. So this new picture of space-time gives us this really cool concept, the light cone. For any event, let's say a star exploding, the cone maps out its absolute past and its absolute future. Everything inside the bottom of the cone could have possibly caused that explosion, and everything inside the top cone can be affected by that explosion. It's like the ultimate boundary of cause and effect in the universe. And this is a brilliant way to picture it. If the sun just vanished, this instant, the Earth would keep orbiting it for a full 8 minutes, totally oblivious. Why? Because for those 8 minutes, we are outside the future light cone of that event. Nothing, not even gravity, can travel faster than light. And this new, dynamic, warped space-time, it actually solved those old paradoxes. The universe couldn't be static. And sure enough, Observations from astronomers like Edwin Hubble proved it. The universe is expanding. The light we see from distant galaxies gets stretched out or redshifted because the very fabric of space is carrying them away from us. Okay, but to understand where all this expansion began, we have to leave the huge cosmic scale of relativity and take a journey to the other extreme, into the impossibly small, totally bizarre, and counterintuitive world of quantum mechanics. The cornerstone of this weird world is Heisenberg's uncertainty principle. Basically, it says there's a fundamental limit to what we can ever know. You can know a particle's exact position, or you can know its exact momentum, but you can never, ever know both perfectly at the same time. The universe, at its core, has a built-in fuzziness. Now, this fundamental randomness, this idea that the universe, at its most basic level, is governed by probability and chance, well, that was just too much for Einstein. He couldn't accept it, and his famous objection summed it all up perfectly. But as it turns out, all the evidence suggests that God does in fact play dice. And nothing, I mean nothing, captures this quantum weirdness better than the famous double-slit experiment. So if you fire tiny particles, like electrons, at a screen with 2 slits in it, you'd expect to see 2 simple lines on the detector behind it, right? But that is not what happens. Instead, you get this complex interference pattern, just like a wave would make, which means that each single particle is somehow going through both slits at the same time, existing as a wave of possibilities until the moment we measure it. It's wild. So how do we get to the very beginning of time? Well, we have to take these 2 great pillars of modern physics, Einstein's relativity for the super big and quantum mechanics for the super small, and we have to bring them together. Our standard model is the hot Big Bang, and it tells this amazing, coherent story of a universe that was born from this unbelievably hot, dense state. And as it expanded, it cooled down, allowing particles to form, then atomic nuclei, then the first atoms, and eventually the stars and galaxies that we see all around us today. But there is a massive problem. If you run the film of the expanding universe backwards, everything, all the matter, all the energy, it all converges to a single point of infinite density and infinite temperature, a singularity. And at that point, all of our known laws of physics just break. They stop working. Science literally cannot describe the beginning. This is where Hawking made his truly revolutionary contribution. Using the ideas of quantum mechanics, he proposed that maybe you don't need a singularity at all. The universe could be finite in time, but have no beginning, no boundary, no edge to fall off of. Think about it like the surface of the Earth. You can travel all around it, but you'll never find a starting point or a hard edge. Hawking's proposal is it's breathtakingly elegant. A universe that is completely self-contained, governed by the laws of science, with no beginning and no edge. As he famously concluded, in a universe like that, there's nothing left for a creator to do. And it leaves us with this final, profound thought, sitting right at that line between physics and philosophy. If the universe just is, what does that really mean for our place within it?